All right, here we are with lesson number 3 of 4 lessons in this unit on thermodynamics. And so far we've looked at concepts like temperature, heat, thermal expansion, which has been a pretty good review of some of the concepts we would have learned in grade 11 physics. We've also investigated gases, which for some of you may be a little bit of a review of what you might have covered in grade 12 chemistry, or even grade 11 chemistry. But moving forward now, we're going to talk about how these things fit together. And lesson 3 is about the first law of thermodynamics, and the second law of thermodynamics is covered in lesson number 4. So we're looking at the first and the second laws of thermodynamics. To begin, though, before we can talk about the first law, we need to recap work, and we need to look at these things called PV diagrams, or pressure volume diagrams. Okay, so again, consider gases and liquids and some of the gas laws that go into place. So here's a thought experiment. We take a gas and we place it into a vessel here. Okay, and this system up here is a piston, and this piston can move up and down. Okay, and as seen initially, here's part A. Here's section A. The gas is in equilibrium. It occupies this volume given by this cylinder. It's got a certain pressure, and it's acting on the walls of this enclosed space. Okay, this disk, of course, has a cross-sectional area of A. And let's assume just for a moment that the gas expands, as seen in part B, in little diagram B here. And when this gas expands, of course, the piston goes up, and it moves a distance delta y in the upwards direction, and that increases the volume delta v. Okay, so the gas pushes up on the piston a distance y, and the volume expands by a change in delta v. Okay, well, what we know is that this change in volume, this little extra bit that we get in this section right here, is equal to the area, the cross-sectional area here, times the change in height, which is here, because of course it's the volume of a cylinder. So this cross-sectional area times this height gives us our change in volume. Okay, so we'll just keep that in the back of our minds for a moment. Okay, so we know though that the gas has exerted some force on the piston because it's caused it to move. And a force applied through a distance, well, that's the definition for work. Okay, so we can determine the amount of work that the gas has done on the piston if we simply say that, well, work is equal to force times this distance. Well, we know what the distance is. It pushes at a distance delta y. We also know what the force is, because in our first lesson we said, oh, well, force is just pressure times area. And if we use our relationship, area times delta y, that's equal to the change in volume. So the work that's been done is equal to the pressure in the gas times the change in volume. And you'll notice in this little formula, which is one of your AP formulas, we have a negative sign. And that negative sign is there for convention. And we'll talk about it a little bit later on in the unit, and you'll see why it's there. But there's a little bit more to this story than simply saying that work is equal to pressure times the change in volume. Because you may have noticed that as that gas pushes the piston upwards, the volume of the cylinder changes, yes, which is expressed right here, but the pressure also changes because that gas spreads out. And that complicates matters a little bit. In fact, we could have, if we were to graph pressure versus volume, at the initial volume we'd have some pressure, but then as the volume expands, the pressure would decrease. And so we might have something that looks like this. And in order to determine the work based on a changing pressure, we would need to use something called integral calculus, which is a little bit different than derivative calculus. But integral calculus really helps us find the area underneath a curve. For our purposes in this course, because it's an algebra-based course and not a calculus-based course, we're going to determine the total work that's done by the gas using these PV graphs. The work that's done in any process going from some initial state to some final state is simply the area under the curve. Okay, so here's our first example. This figure here, from some initial state at this initial pressure and volume, navigates or makes its way to this final state at this pressure and volume. Okay, and what we want to do is, so we want to determine the work that's done by this fluid during this process. Okay, and in order to do that, we need to figure out the area that exists under this curve, and that's going to tell us the work that's done by the fluid. This gas is expanding, or this liquid is expanding in its volume, and so that means that we're going to do some work. So in order to do this, we need to calculate the area in this section of the graph, the area in this section, and the area in this section, and we'll do that now. So for this first section right here, we know the pressure that it's at, and we know the change in volume that it experiences. So the work done in this section is pressure times the change in volume. And of course, this is just a horizontal line. So this is easy. It's at a constant 6 times 10 to the 6 pascals. Again, we're using pascals because this is the SI unit for pressure, and we're using meters cubed because this is the SI unit for volume. So we got 6 times 10 to the 6th. Our change in volume, it goes from 1 to 2, so final state minus initial state. And we get 6 times 10 to the 6 joules. In section number 2, this is a little bit different. There's this little triangular area, and then there's this little square or rectangular area down here. And so we would say that the work that's done in this second section is, of course, the base times the height divided by 2 for this triangle, plus the length and the width times the width of this rectangle. We can sub in these numbers. The base of this triangle, you'll see right here, is the change in volume, which is going from 2 to 3. The pressure, the height of this triangle is, of course, the difference between 2 times 10 to the 6 pascals and 6 times 10 to the 6 pascals, so 4 times 10 to the 6th. And we divide by 2. We add to that, of course, this pressure times this change in volume, and we end up with 4 times 10 to the 6 joules. We now find the area of this small section down here, section number 3. Constant pressure times the change in volume, 2 times 10 to the 6 joules. And the total amount of work that's done by this fluid is, of course, the sum of these 3 areas. And when we add this up, we get 12 megajoules. So that's a lot of work that's been done by this fluid. 12 megajoules of work. All right, so now let's get to the first law of thermodynamics. In short, the first law of thermodynamics is a generalized statement of the conservation of energy for any system. Something that we've ignored in physics is the internal energy of a system. And when I say in physics, I mean in our study of physics. We've never really considered that. You know, when you talk about grade 12 physics and when you talk about grade 11 physics, we talk about the conservation of energy, and we don't really consider internal energy of any object as being very important. But when you're considering a system that can have a change in that internal energy, then it's an important aspect. Like when a block slides down a plane, and we do this using energy methods, we usually don't consider the amount of heat that the block picks up and how that would affect the internal molecules in the block of wood. We just don't consider that. We never have. And really, for all intents and purposes, you probably wouldn't. But let's look at these 3 aspects, because these are very, very important. the internal energy of a system is basically the energy within a system. So it's like the molecules and their motion, right? So this all has to do with the kinetic molecular theory, right? So when the energy within a system is important and we need to consider it, as we do when we're talking about thermodynamics, this needs to be included in the conservation of energy. Heat, we've of course talked about already, but that's the transfer of energy, of course, due to some difference in temperature. And work should be well known to us. This is the transfer of energy to perform some useful task. So combining these three things right here, we can write the first law of thermodynamics in the following way. The change in internal energy is equal to the change in heat energy plus the change in work. Okay, so the internal energy of our system is affected by the heat that either flows into or out of our system and the work that the system does or is done to. Okay, and one of the important things before we can solve any problems is something that we need to take note of, and that's sign conventions, because energy can be negative or can be positive, but usually positive energy and negative energy have to do with the flow of energy either into the system or out of the system. So internal energy, which we give the symbol U, when the internal energy is positive, that basically means that temperature is going to increase, because the internal energy of a system, we know from kinetic molecular theory, the internal energy of the system has to do with molecular motion, and molecular motion has a lot to do with the kinetic energy of molecules, which has a lot to do with the temperature inside that system. When U is negative, in general, temperature decreases. Okay. Now it's important to note, just before I go too much further, these are the conventions that we're using in AP Physics. Okay. When you get to university, these conventions may be a little bit different, right? Because that's one of the things about certain textbooks will do things in certain ways, because this course is for writing an AP Physics exam. I try and adhere to the conventions that are set out for the AP Physics exam. But don't be surprised, these conventions might change. All right, Q, heat. When heat is positive, or when this quantity is positive, it means that heat enters the system. So when you have heat flowing into a system, Q is positive, and when heat flows out of a system, Q is negative. Work is very similar. When work is positive, it means something is done or work is done on the system. When work is negative, it means work is done by the system. Okay, so here's example number 2. A gas is compressed from 9 liters to 2 liters at a constant pressure of 0.8 atm. In the process, 400 joules of heat leaves as gas. 400 joules of energy leaves the gas as heat. What is the change in the internal energy of this system? The change in internal energy of the gas. Well, we're given lots of information here. So we don't know how much work is done. We do know how much heat leaves the system, and of course we've got our negative sign here because it's leaving. The internal energy is what we're looking to find. So the question is, can we determine work? And because we have information about volume, and we have information about pressure, we absolutely can determine the work. We need to convert these units of volume. 9 liters and 2 liters is not SI units, so we convert them to meters cubed. ATM, atmospheric pressure, is of course not SI units. We convert that to pascals. All right. We see this as we introduced earlier on in the lesson, and you're going to notice right now why this negative sign is crucial because of our conventions. This is a compression, okay? And any compression, here's our pressure, right? But here's our V2 minus V1. And of course, you'll notice that in any compression, V2 is going to be smaller than V1. And so if we've said that work done on the system is positive, then this negative sign has to be here, because any compression is going to have V2 being less than V1. This bracket is going to give us a negative number, and we need that to cancel out. Because work done on a system is compressing the system, right? We need to do work on that system to get it to do that. So that's why, because of our convention, we've got this negative sign here. All right, when we work this out, we see that the change in work is equal to 567 joules. And we can pop this into our first law equation. We can say, okay, the work minus the heat is equal to the change in internal energy. And of course, this is 167 joules. Because this is positive, means the temperature of this system will increase. All right, so let's talk about a few thermodynamic processes. Because there's several different processes that may be applied to a system. We're going to cover a few of them now. An isothermal process is anything that takes a gas through a change at a constant temperature. So here, there's no change in the internal energy of the system. So this is isothermal. Isochoric is also called isovolumetric, okay? But that's basically any process where we have a constant volume. And with constant volume, that means no change in work, okay? Because there would be no area underneath that curve. Isobaric is any process that applies a constant pressure. And adiabatic is any process where no heat is transferred into or out of the system. And these are kind of the four processes. Now, on a PV diagram, they will all look a little bit different. And we can go through a couple of them now, just so that you're familiar. All right, here's example 3. A 1 kilomole sample of helium, which we can treat as an ideal gas, is taken through the process shown in this diagram. Path BC is isothermal, which means anything along this path is at a constant temperature. So this is what we want to know. What are the temperatures at point A, at point B, and what is the volume at point C? Okay, we know this. We know the pressure at B. We know the pressure at A. We know the volume at A and B. We know the pressure at C. But these are the three things that we want to know. So let's begin, because we can use the ideal gas law here because helium's an ideal gas. So to begin, at point A, we know the pressure, we know the volume, and we know the number of moles. So we can find the temperature. And let's do that. PV equals nRT. And when we rearrange and substitute for our values, you'll notice this is the moles down here. And then here is, of course, R, gas constant. We can solve, and we get 577 Kelvin as our temperature. We can also solve for the temperature at B, but we're going to use a proportion. Instead of using just PV equals nRT, we're going to use a proportion. So here it is right here. We've got pressure at A times the volume at A divided by the temperature at A is equal to the pressure at B times the volume at B divided by the temperature at B. This is because the number of moles in the system is constant and R is a constant, so we can say these two things. We can rearrange this, and we also know that the volume at A is equal to the volume at B. And this is really what we need to extract out of this, is that, oh yeah, those 2 points, A and B, are along an isochore, right? Which is an isovolumetric, a constant volume line, okay? And so what we'd say then is that, well, we can cancel out VA and VB and just rewrite temperature and solve 1150 Kelvin is the temperature at B. Okay. We can do something now very, very similar, solving for VC. We can say pressure at B times the volume at B divided by the temperature at B is equal to the pressure at C times the volume at C divided by the temperature at C. But because the path B to C is an isotherm, we know that the temperature at B equals the temperature at C. We can rearrange, and you'll notice these two things cancel out, and we get 80 meters cubed as the volume at C. And that is basically how we work thermodynamic processes, the first law, and how we incorporate some gases.